Okay, so I did an insert of 4 ahead of the end. I got back an iterator for that element that had just been inserted, but then I increment that iterator so that I'm, quote, pointing at, unquote, the end again. So the next iteration within the copy algorithm is going to take the 7, insert the 7 just ahead of the end, get back an iterator, quote, pointing at, unquote, that 7, and then bump that iterator to the end. The upshot is, by the time this is all done, and I use my range for loop to display the contents of D, I will simply have, within the deck D, 471349 copied from the vector V. In the second copy algorithm, once again we're copying from V, this time into S. We're using an inserter on S with S.end as the starting position. Now, because S is a set and S maintains its own ordering rule, in effect the S.end is virtually ignored, and as we go through and do the copying of 471349 into the set S, those end up in the set S in ascending order with no duplicates. So when I display S, I just have 13479. Okay. When we use the transform algorithm, we saw that we could use the same container both to provide the source information, that is, from its begin up to but not including its end, and also to provide the output container. Insert, though, is not as tidily behaved as the overwriting that we were doing of existing elements when we did transform. It turns out that if you insert a new value into a vector or into a deck or into some unordered container, like an unordered set or unordered map, if you already have some iterators sitting around, quote, pointing to, unquote, various elements within the vector or deck or unordered container, then as a possible consequence of new memory being allocated, because you're expanding your vector, you're expanding your deck, you're expanding your unordered container, this may invalidate all of those previous iterators that you had. In fact, you really need to assume that any insertion that you do into a vector, deck, or unordered container does invalidate all of these iterators. Here on slide 20, I have an illustration of what problem we can run into. For example, we're declaring an initialize V as a vector of int containing 471349, and when we display that on slide 21, we simply have 471349. But if I use the copy algorithm to copy from the vector into the same vector at the beginning, well, each time I insert a value into the same vector, that messes up the positioning of the original elements. Everything gets shoved over one place to the right. And so what typically happens is that the first value from the input vector, in this case a 4, does get copied in place at the beginning of the vector correctly. However, all the remaining values, in this case 71349, may not get copied over correctly because they've been moved around. And so in my case, on my machine, following the 4, which is inserted in the correct place, I basically have garbage. 1 and then minus 2 billion and something, and then another 1, 32, and 0. So be warned that for something like a vector or a deck, where either all of the elements or many of the elements may be stored in contiguous memory locations, doing an insert is going to move everything around and therefore mess up any iterators, including those used internally within algorithms like copy. Now, if you have an associative or tree-structured container, then all of the values are allocated as individual nodes hooked together by pointers, and it turns out that it's always safe to insert from an associative container back into the same container. Although, if you have a set and you take an element from the set and insert it back into the set, since the set doesn't allow duplicates, nothing will happen. Similarly with a map, which only allows unique keys. So it's only for the multi-set and the multi-map that it makes any sense to talk about inserting values from the container back into the same container. Here on slide 23 we have some example code. I'm setting up a multi-set containing, surprise surprise, 471349. I'm displaying that with this red range for loop, and what I get is those 6 values in ascending order. Duplicates are allowed, so I have 1, 3, and then 4 twice, and then 7, 9. If I copy from the multiset using an inserter back into the same multiset, this works fine because adding new elements to the multiset does not move around any of the existing elements that were in the multiset, and consequently I just end up with a revised multiset that has all of the elements twice as many times. So I have 2 1s, 2 3s, 4 4s, 2 7s, and 2 9s. On slides 25 and 6, we have another example program making use of general inserters, and the output from this program is shown here on slide 27. Now, on slide 25, we're just showing the top part of main below all of the headers that we need to include. So we have our good old vector event V initialized with 471349. We have a deck event D, which is empty. And what we want to point out in this program is that if you're using general inserters, you can set up your insertion at the begin or the end, but you're not restricted to that. You can set up the insertion to occur somewhere in the middle of a container. So here's on slide 26. Here we are copying from the vector V, v.begin up to but not including v.end. We're inserting into our empty deck D at the end. So each element is going to be inserted at the end as the deck D grows, and so when we display the deck D after we've done that copy, we have the same elements in D, 471349, that we started out with in V. But in this next copy algorithm, the copy algorithm in red, notice that we're setting up our inserter again for the D deck, but instead of inserting right at the beginning, we're inserting at the beginning plus 2. Now, a deck has random access iterators, so it's perfectly legal to take an iterator, d.begin, and add an integer offset to that. So this is going to end up inserting not ahead of the first element in the deck, but instead ahead of the third element in the deck. And what we're copying in, as we did in the blue copy, is the contents of the vector V. So this time what's going to happen is that the contents of V, 471349, end up getting copied in ahead of what had been the third element of the deck, that is the value 1. And then finally, as a final example, notice that this time our copy is using reverse iterators on V. So we're going to be copying from the 9 at the end of V to the 4 at the beginning of V. And we want to do this insertion right in the middle of D. So we can say, let's do our insertion at d.begin plus d.size over 2. Okay, so d.begin plus d.size over 2 will give us an inserter that's in the middle of D. And sure enough, what we see is that we end up with V in reverse in the middle of D, 943174. And there are 6 values in front of that and 6 values after that. So, back inserters, front inserters, general inserters, and the copy algorithm provide a lot of power and flexibility based on what seem like pretty simple ideas.